Here we go. All of your lines should be muted. We're going to have chat breaks throughout the presentation, but we're going to primarily use our chat box to collect your questions. So feel free to, as something comes up and you're curious about or have a question or something, go ahead and type it in at any time. Or if you're noticing some technical issues or something like that, we'll be monitoring the chat. So hopefully everything goes well as far as connectivity and technology today. And we are going to hopefully get these recorded and posted. So if you do have to drop out, we can get them posted and you can watch it later. And we do have some other, or we are going to post some resources in the chat box. Looks like those did get cleared from before, Casey. So we'll probably post, or if you want to throw them up there now, Casey. We'll put some reference documents in the chat at some point. If we can get them on there, yeah, he's getting some uploaded now that you can, hopefully you should be able to click to download. We've got our full actual administrative rules, which is chapter 73 of Iowa Administrative Code. That's really a go-to document for our permitting and our entire program. And then we've got some other technical resources there that Casey will probably touch on as he goes through today's presentation. So as you got some time, you might click and get those downloaded, and those are, not sure if all of those are currently on our website, but we can get those posted as well. So if you don't happen to get them downloaded today, we'll try to get those posted and available. So with that, oh, Casey, that might have still just gone to me. I see it's a direct message. You might have to switch your chat to full public and maybe repost those if you've got a minute. I guess while he's getting us posted again on the non-direct chat, I'll just keep talking. So there's our primary dam safety staff here at the DNR. Like I said, I'm a supervisor of the section. We've got Casey, and then many of you have dealt with Ashley as well, Ashley Campbell. So with that, I'll turn it over to Casey.
Thanks, John. It should be posted now. We haven't done webinars for a while, but we did back in 2020. We did a series of webinars. Just a quick recap. There's a large number of dams in Iowa. They have many purposes. Dams can fail and cause damages if they're not maintained or constructed properly. The DNR Dam Safety Program regulates these dams, or regulates some dams in Iowa to reduce that risk. Maintenance is important. Repairs are expensive. We did a quick webinar on how to find and hire an engineer. And then our latest one was a summary of the rule changes for dams that we did in 2021. That's the chapter 73 that was posted in the files, and we'll send out again. That one, we went detailed on what changed, what it changed to. We're not going to do that again today. We'll hit some of those points, but we're not going to go line by line through the rules and say what changed. So quickly, an overview of Iowa Dam Safety Program. We have 4,200 dams in our inventory. Those are the ones that we regulate, and we'll go over what those thresholds are in a little bit. So these dots are all the inventory dams. The blue ones are low hazard, red ones are high. The yellow ones are the significance. We do permits for new dam construction and modifications. We inspect about 100 dams per year. We conduct risk analysis and do owner education. And then last, compliance and enforcement. So low head dams used to be a section in the rules. We changed it with our dam rules that we updated and called them structures or materials across the channel. So those are the ones that don't meet the thresholds for a dam. We would call them a structure or material across the channel. Those are still in chapter 72. The criteria for those didn't change. We won't read those, but it hasn't changed. This webinar is not going to be about low head dams, and we'll just focus on embankment dams. So to start our overview, we'll start out with dam thresholds and water storage. Our thresholds we changed on, it used to be pretty complicated depending on where you were, rural, urban, emergency spillway or not. So we got rid of that. We switched it to match with the National Inventory of Dams. So if the height is greater than 25 feet or the storage at top of dam is greater than 50 acre feet or any high hazard dam, they're regulated by the DNR. We have some exclusions based on if it's less than 6 feet or less than 15 acre feet, they're not large enough to need to be regulated or to cause a safety risk. So those ones are excluded. There's not many that hit those. So we added the high hazard criteria, which is a harder thing you can't just measure. But it's easier to estimate hazard classification now with various tools. But generally, a dam to be high hazard would need to be close to a development, near some major roads, near some houses. This could include some stormwater basins if it has a dam and there's houses around it or downstream from it. We still included the roadway exemption, but we modified that to include dams that serve a purpose commonly associated with dams. So it's not a blanket, any roadway culvert, public embankment roadway culvert gets an exemption. Not if it's designed to be a dam, then it probably is a dam. So here's an example: roadway culvert, dam. It is a pipe under the road, but that it's intended to be a dam. Water storage. A water storage permit shall be required for all regulated dams to legally impound water. It's no longer a separate application form. When you apply for a dam construction permit, that includes your application for a water storage permit, and the water storage fee has stayed the same at $75. And that's for any regulated dam, not just a certain different threshold that it used to be. In order to get the water storage permit, the criteria is that it has to be a beneficial use: water supply, flood control, recreation, some sort of beneficial use to the water. And it needs to not adversely affect protected flows that are listed in chapter 52. There's a short list of streams that need to have a minimum flow. And for a higher significant hazard, the water storage permit is not issued until we receive as-built plans and a construction report. So our design guidelines used to be in Bulletin 16, which was a separate rules reference document. It was 30 years old. It needed some updates. So we decided to put all of that in Iowa Administrative Code, Chapter 73. So there's no more external rule reference document. We have the prescriptive design requirements have been relaxed. So it doesn't tell you top width, side slopes, core trench dimensions. It doesn't tell you all the specific things that need to happen. We would have ended up with a document the size of TR60, so why don't we just let people use a reference? So some references that we'll talk about today: FEMA Conduit Manual, NRCS, TR60, FEMA Design Flow. And we'll talk about these as we go through those sections. So preliminary design, you have an idea. The owner has an idea. Hey, I want to build a pond. You need to know, where do you want it to go? And why do you want it? flood control, recreation, what are you trying to do? And then the most important step, probably the first question, when somebody calls and says, hey, I want to build a pond, other than how big is it, my next question is what's downstream. So the hazard classification is important, but it's an iterative process because you don't know how big your dam's going to be, so you don't know what the consequences are. So we need to make an assumption. What's the hazard class going to be before you can make a guess on how big is the pond? For that, you probably need some preliminary hydrology and hydraulic calculations to get your initial sizing. And then check again, is that really still a low hazard? Is it significant? Are we flooding people? So hazard classification and dam breach. We don't know the hazard that the dam causes without estimating the breach. But we don't know the design criteria until we know the hazard classification. And we don't know the hazard classification until we know how the dam is, how big the dam is. And it's just a circle. You gotta guess, take a try, see where it ends up. So hazard classification is a rating of the dam based on the potential consequences of a dam failure. They are low, significant, and high. And it's not a reflection of the condition. It's only the risk downstream or the importance of the structure. Here's a handy table. High hazard, loss of life is likely to occur. Significant hazard would be no loss of life, but structures could be damaged due to the failure, utilities, roads, or it could cause significant economic losses or public damages. And then low hazard would be everything else. So no loss of life, low economic, and low public damages. Here's an example of a low hazard dam in a farm pond situation, nothing downstream, gravel road, flows right into a larger stream. Here's a significant hazard dam in Ankeny, major roadway there. Not expected to fail the road if the dam breaches, houses and development downstream. And then a high hazard example, this is a dry dam down on the bottom left, upstream of a city, and there's significant flooding that would occur due to a breach of that. So how do we predict dams to fail? There's two main ways that an embankment dam will fail, and that could be internal erosion or overtopping. There's some pictures of each. Internal erosion, water seeping through the dam, creating a path, or overtopping and creating a head cut. So a couple of dam breach scenarios to look at is the sunny day. That would be just a normal day, water level at normal pool. Nobody's expecting flooding that day, and you develop piping, it's internal erosion, and the dam fails. And then the other one would be an overtopping failure. That would be the dam fills up, water goes overtops the dam. It takes about a foot of overtopping to initiate the breach, to get the vegetation cover broken down and erosion started. And then we would see what consequences, and you can check for incremental damages and see if the same storm that caused the overtopping would already flood people, because generally that's a bigger storm. And then once you have those two breach scenarios, to estimate the consequences, the Bureau of Reclamation has this ACER 11 hazard classification guidelines, and it has some charts in it that shows depth and velocity correlated to a low danger, judgment danger, high danger zone. This one is for houses on foundations and adults. There's one for kids, mobile homes. I think there's one for campers. And you can look up check your depth, velocity, and see where see where it lies in there. Couple methods to do a dam breach. There's a simplified method where you can just check the aerials, look at the top of dam elevation. An estimated dam breach, use some empirical equations to estimate a peak flow. You could also use HMS if you're doing that if you're using HMS to do your hydrology model, you can do a breach estimate in there. You could do normal depth calculations with those empirical equations if you have a specific location, or use 1D HEC-RAS to do a steady state model of the flow downstream. And then more detailed dam breach method would be use those same empirical equations to estimate the dam breach parameters, the width and the time to initiate the breach. And you could do that in a 1D HEC-RAS unsteady model with the hydrograph, or you could use a 2D model, HEC-RAS or any other 2D model to model the breach, discharge, and flows. So here's a FEMA guidelines for inundation mapping. They have the same sort of table. They call it tier 1, tier 2, tier 3, but it's similar screening levels. And that document gives you some guidelines on what you should look at downstream and how to do the modeling. So here's an example of a basic breach method. Farm pond again, nothing downstream. Flow path generally goes down to this other creek. There's nothing in the path. There's a road here that maybe is gravel, looks like gravel. There's a house on this side, but it's up high, so that would be a low hazard. Here's an example of a dam upstream of a city, and it would breach right through the town, right through the city. So many houses, it's a flood control dam, it's made to hold water. So that's clearly high hazard. You wouldn't need a breach analysis for determining hazard classification. To estimate the dam breach, there's a document from the state of Colorado that has some dam breach guidelines. There's a link to it here that's in the slides too. Guidelines for dam breach analysis. They revised it in 2020. They also included a spreadsheet where you can put in some dimensions of the dam, height, storage, volume. Yeah, I said that. Crest width, like the width of the dam. And then it will tell you a couple parameters. There's two spreadsheets that they made. One is the Froelich method and the other is McDonald language monopolist. Those both have, it also tells you in that Colorado document, they tell you which ones you should use in different scenarios. Like the Froelich method, that data was, the failure data was created with failures that had 100 acre feet or more. So if your dam's smaller than that, you probably shouldn't be using the Froelich method. The equations are listed out here. You don't need to go through those. To estimate the formation time, average width, and a peak flow. So to do an estimated dam breach method, here's an example of a subdivision with a dam in the middle of the subdivision. And they wanted to do, in this case, they wanted to do some upgrades and wondered what their unpermitted dam needed to be upgraded to. So we could see that there's houses downstream. There was a road downstream that was going to block the flow with the culvert. This house on the left side of the picture with the pool has a walkout basement, and it was sitting kind of low. So using those spreadsheets to estimate a peak flow, did a HEC-RAS 1D, just a steady state model to check that culvert flow. The culvert is what backed up the water into this house. It was a foot deep. We estimated it would flood for 15 to 20 minutes. So since flooding was expected at the house, flooding and damages at the house, it was called significant hazard. And then the same for the detailed breach, you would start out with those empirical equations. And then typically now, instead of doing a HEC-RAS 1D unsteady, that is more complicated to get working. HEC-RAS 2D is much easier. So typically I'll use HEC-RAS 2D. And use that spreadsheet to get the breach width to put into HEC-RAS and a formation time. You can put that into your storage connection. You can either just use those values from the spreadsheet, or in RAS it has those same equations, where you can just pick which one you want to use and it will populate them. And then you can plot water surface, all your normal HEC-RAS mapper features: water surface, elevation, depth times velocity for your different plane runs. You can do Google Maps and bring in your own layers. There's an example of velocity. And then another tool that is kind of newer to us is a dam breach. It's called DSS-WISE. We use it as a screening tool. It was developed, FEMA funded it, developed by the University of Mississippi. It's a web-based 2D model, and it has the NID dams loaded in there that you can import existing dams. It uses the NHD terrain data. The new Iowa 2020 LiDAR is in there. A limitation is you can't do any terrain modifications. So if you're excavating your pool, that can't be changed in there. Or if you're looking at downstream of a dam, putting in a development, you can't put in proposed grading. It only does the LiDAR. And we usually use that for screening. It's very simple to use, very easy, very fast, but it doesn't have a lot of output, like model output. We don't know. You can't review inputs or outputs and see what is the model doing. You just get a map, click the button, get a picture, and it looks good, but there's nothing to review. So here's an example. This is labeled Parkview Lake. That's in Urbandale. This one, the dam was picked, Parkview Lake. It brought in the normal. You have to put in the elevations. It brought in the normal pool volumes, maximum volumes. We draw the dam crest. You can pick the breach equations that you want to use to get your average width and your formation time. Tell it how big of area you want to look at, big or small. This was just an example that was way too big. But then your cell sizes could be as low as 15 feet, and you can go bigger if you need it to run faster. Here's an example, some screenshots of the output. This one doesn't have the runtime, 141. This one took 2 minutes. It looks like from start to stop. Here's an example of the depth grid that you can see going through the city. Oops. You could also look at the terrain data instead of an image. And here's some other examples. This is maximum depth times velocity max. And it also has, you can kind of see it on the bottom of the pictures, there's human consequences. So it will take the depth. It uses the depth, the velocity, and the depth times velocity and creates these areas. On the left is the areas hazardous to people outdoors. I think that goes from low, medium, high, and high, something like that, just based on those Is it really fast? Is it really deep? And then the other one I have turned on the right, potentially lethal flood zones, that would be children and adults. And I think that one is just based on dB. So this gives us a quick thing to see, a quick tool to see, do the results make sense of the dam breach? It's a good check. It's also a good screening tool to see, are you clearly out or are you clearly in? And that, I'll go back a second. That is run through FEMA. You have to request permission to get into it. That comes through us at the DNR. So now some hydrologic and hydraulic criteria. We have design floods for the dam, freeboard design storm based on hazard classification, and it's what sets the frequency of overtopping that's allowable. And then the spillway design storm, also based on hazard classification, is the frequency that the auxiliary spillway is used. So the freeboard design storm shall pass floods without overtopping of the dam, or the dam should be designed to withstand the overflow. We've taken out the old criteria for no auxiliary spillway, so you can, no matter what you design, you can set the freeboard design storm at the peak. You can set your dam top at the peak of the freeboard design flood, with or without an auxiliary spillway. And then the spillway design flood should be passed without need for the use of the auxiliary spillway. Here's a table that's in the rules of the different design storms. So the freeboard for the low hazard is the 100-year, 1,000 for significant, and PMF for high. And then the spillway design floods are the 10, 50, and 100-year. To get the depths for those storms, NOAA, National Weather Service, their Hydrometeorological Design Center has links to what to use. The probable maximum precipitation documents is listed, and it comes with a map that shows you which ones to use based on what state you're in. So what's my next? Yeah, Iowa is HMR 51. The PMP, probable maximum precipitation, that's the greatest depth of precipitation for a given duration that's physically possible over a particular drainage area at a certain time of the year. So in the east of the Rockies, we are in HMR 51. There's different depths that you would use based on your drainage area from 10 square miles up to 20,000 square miles. And they're based on climate assumptions and storms from the 50s. So very simplified, the PMF is based on the maximum moisture content of the air, and that sets how much could possibly come from a storm. So climate changes with increasing temperatures, that increases the moisture content, which is making PMF, theoretical PMF values should be going up with that. The state of Colorado, I've got a picture of their document down there. They have, I'm trying to see a date, it was like in the 2020s. They added a moisture factor, so they require all storms to be multiplied by 1.07 to account for changes in the future. There currently is a national committee reviewing updates to the PMP. I have a link to that group and what they're working on in the slides. You can sign up for a mailing list at that link, and they send updates kind of regularly on the meetings that they're having. Some of them you can watch. And then the frequency storms, NOAA Atlas 14 is the current rainfall source. They have a web viewer that you can go to, pick Iowa. You can zoom in on your location of your project or drainage area, and it will give you recurrence intervals and storm durations. So you can look up in a table 24-hour, 100-year would be 7.4 at this. It has, they added the 1,000-year and 500-year, which is helpful. SUDAS was updated a few years ago to be based on this Atlas 14 data. It doesn't match exactly if you were to go pick the point, but it's close enough that you could use the SUDAS data for your region. Storm distributions, typically the type 2 has been used. That was developed by the SCS in the 1970s. They're 24-hour storms. It's a typical thunderstorm, light rain, huge peak, light rain again, storm's over. They revised these, the NRCS has revised these in 2015. Iowa is in the Midwest Southeast region, so MSE 3 and 4. And I think there's a little corner of little dot of 5 somewhere. Basically the same. They're a little bit different, but it's still a sharp peak in the middle at 12 o'clock. And then another one is a Huff distribution. That is a time distribution of heavy rainfalls or heavy rainstorms that was developed in the state of Illinois in the 90s. It has different quartiles, whether it's in the first, second, third, or fourth part of the day. But these would be good, or these could be good distributions for PMF. And I've got some examples here showing, kind of hard to see, but on the top, depth versus time. So the purple is the Huff, and you can see it's just a steady rain pretty much all day long, like your normal long daily rainfall. And then the MSE3 and the type 2 are the green and red, and they're basically the same with that big spike in the middle of the day. So once you have your rainfall, then you need to turn that into runoff. So we need rainfall losses. To get that, we usually use the NRCS TR55 method. You need a curve number to do that based on the land use. And then a time of concentration. Typically, we'll see the curve number method. That's just based on basin length, watershed slope, and curve number. Or you could use the NRCS velocity method, where you would add up your parts of sheet flow, shallow concentrated flow, and open channel flow, or multiple open channel flows. There used to be a recommendation of 300 feet of sheet flow. That's been changed in 2001 to limit that to 100 feet. Don't get too many of these coming in, but still rarely we'll get a couple of those 300-foot sheet flows in a year, which gives you a really long, nice long time of concentration and a nice low peak. But you should limit that to 100 feet. And then the open channel flow is a little tricky because it's iterative. You have to put in the wetted perimeter and a flow area. You don't know what that will be until you're getting a peak. So you might have to do some testing there, run it and test it, then see what, run it again. The StreamStat, USGS StreamStats is a good web tool to get some flow estimates from regression equations. And it also has some other basin characteristics that you can look up. So if you zoom in to your watershed, pick the point of your project, it will give you a basin area, and that's based on the 10-meter DEM. And yeah, it's not just for flow estimates, it's got really good basin data in there. But you have to turn on all basin characteristics once you start to make that report. And when you do that, you can get drainage area in square miles, you can get a basin length, using ArcHydro. So from the longest flow path, is what that is, longest flow path in the watershed to your point. And then you can get the mean basin slope from the 10-meter DEM. And you can get soil types. You can't get curve number, but you can get soil types, A, B, C, or D, or fractions of each. Using those, you can do the curve number method pretty quickly because you just need the slope and the length and a curve number. So StreamStats makes that pretty easy. And then last thing with the design storms is we added a incremental consequence analysis section to our rules. So you can reduce the design storm based on incremental consequences. You need to show a negligible increase in water surface velocity consequences due to failure when compared with no dam failure. And in that section, there's some minimum freeboard design floods that you can't go below just based on their hazard classification. So the high hazard freeboard design flood could be reduced from the PMF as low as the 500-year or somewhere in between. And then the significant and high can't go lower than the 100-year. So the low one doesn't change, but the significant you could lower from the 1,000 to a minimum of the 100. We haven't received any designs that include this since we added that rule, but we've had some questions about it, and we've had some people. I think the engineers wanted to do it, but then the clients didn't want to pay for it for the extra analysis. I've got an example. Let's pretend project that we're building a new dam. Over on the top is an aerial photo. We're going to pretend build this dam here. It's a dry dam, flood control, and we're going to set the top at the freeboard design storm, not add extra freeboard. And have a 3-foot deep auxiliary spillway over here on the left side of the dam, bottom of the pictures, which flow directly at this building that we're going to call a house. It's not a house. We're pretending it's a house for this. So it's got those spillway flows headed right at the house, assigned to the PMF. And we do a dam breach where this red, I think you can see my cursor. We've got a dam breach where this principal spillway pipe is at that red location. For this example, that is actually at the house, but dam breach there. It's got flooding with the PMF. The dam breach shows 6 foot of flooding down at this building. And then the PMF with no breach. So all the PMF flows are coming through the spillway pipe and then through the auxiliary spillway flowing directly at this house. And let's say that shows 5 foot of flooding. So that does not show, basically it's the same. There's not an huge added flooding risk due to the PMF breach. So taking a look at, let's start the incremental consequences. Let's check, we could go as low as the 500-year. So let's check the 500-year, set the top of dam. At the 500-year, add an auxiliary spillway. That should stay the same at the 100-year. And that shows us 3 foot of flooding at the house from the dam breach. But then the dam breach only shows us a 1/2 foot of flooding. So the flows are pretty minimal through this auxiliary spillway. It's not really flooding the house. We show an extra 2.5 feet of flooding at the house from the dam breach. So that is an incremental consequence. Putting the dam there makes flooding worse due to a dam breach. So it needs to be a little bit higher storm. You wouldn't have to, yes, that's incremental consequences. So let's check the Q1000, 1,000-year storm. You don't have to pick a recurrent storm, but just for this example, to make it bigger, we'll do the 1,000-year storm. that shows us type of dam is set at the 1,000-year. We do a dam breach. We've got 4 foot of flooding at the house. If we just route the 1,000-year through the dam, flows through the auxiliary spillway, we get 2.5 feet of flooding at the house. So that's a 1.5 foot increase. So that's no incremental consequences. There's not much difference between a couple feet of flooding in the house and a couple more feet. It's already getting damaged. It's already called high hazard, so risk to loss of life is the same. Velocities, let's say velocities stayed the same. No incremental consequences. So we could, with this pretend example, we could lower the freeboard's design storm down to the 1,000-year. It takes some extra analysis. We haven't received any that have it, but it's a way that if it doesn't make sense to keep raising the dam, maybe the design storms could be lower. Some resources, the Association of State Dam Safety Officials has some webinars that you can watch. They're listed at the training center. Hydrology 101 and Hydraulics 101 are very good beginner level webinars to give you an overview of those topics. They have some more in-depth ones. Some software that we look at or that we receive commonly is HydroCAD, PondPack, WindPond, HydroFlow, Swim, HMS, RAS, any software you could, there's no requirement on what you can or can't use. We would just need to be able to review it ourselves, where we would need you to show us if it's something we don't have, step us through what your model's doing and what's it showing. And with that, we can pause for some questions on design storms, hydrology, breach.
Yeah, so I did get one question, Casey, and it kind of deals with, I think you mentioned earlier that for breach analysis, we usually do a sunny day and a PMF or an overtopping flood event. Are there situations where the sunny day breach would determine the hazard class analysis versus the worst case flood, the highest loading on the dam?
Yeah, right. Yeah, so typically we'll start by looking at the worst case overtopping flood, and that shows flooding from the breach. Maybe look at the incremental consequences and it shows that the floods are the same. Maybe the consequences are the same to the two. And maybe in that case, maybe it doesn't need to be called high because they were already going to flood. But the sunny day permanent pool, maybe that one would control if that one is causing flooding or risk to loss of life in the sunny day. That's how that one could control if you don't show incremental consequences of the larger storm.
Sure, and sometimes that's when you have a pond on a smaller tributary or something too, right? So a lot of times you'll have a main branch of a stream that, yeah, is going to go to flood stage during that high extreme storm event, right? And causes that flooding, and then failing the dam on top of that, like you said, doesn't create the high incremental, but on the other hand, a sunny day failure of a large. So like in your example you just gave, sunny day didn't come into play because it was a dry dam. So if that one did have a normal pool, that could flood. Although, like you said, it was already a high hazard dam either way.
Yeah, and that's pretend. Yeah, right. That is the cases where I've seen the sunny day is the controlling is where there's that stream downstream that is causing also flooding.
Okay. So that was the only question I see punched in. Does anybody, we can take just a second. Anybody else has any questions they'd like to submit? I know there's a lot of a lot of stuff thrown out there. It is, there's a lot to the design process, I guess, the H&H, and trying to kind of dive into it can be a little overwhelming, but like Casey pointed out on those last two slides, there are some additional resources too. If you're newer to H&H, there are some good external references as well to walk you through that. And this is just kind of showing you the main things we're looking for as we check submittals. All right, well, you're gonna have another question break coming up soon or later, right?
Yep.
So if anybody thinks of anything, go ahead and type it in as we keep going, and we'll hit it at the next break.
Okay, sounds good, thanks. Okay, next we'll move on to spillway design requirements. So this is one of the sections where we took out prescriptive requirements. Then we switched to this rule: spillways shall be designed to operate safely for the life of the structure under all flow conditions, including the freeboard design storm. So we need, for the spillway, we need to get water over or through the dam in a safe manner. The sizing of those will depend on the watershed and the size of the lake, which would be the storage, but typically we can look at the watershed ratio of how big is the watershed area, drainage area, compared to the lake size area. Typically a 10-to-1 watershed ratio or 10 to 20 to 1 will be a decent size rule of thumb to have enough water to keep the water quality decent, to keep enough water coming in, but not too big that you don't have to have a huge spillway to get all that water through. The more lake storage you have, the smaller spillways you can have to build if you can catch that volume instead of have to pass it through. A common practice for a dam is 2 spillways. The principal spillway will handle your continuous flows. Usually it's concrete, steel, pipe. It can be controlled or uncontrolled, so with a gate or without a gate. And then an auxiliary spillway, which people commonly call an emergency spillway, commonly will be a grassed waterway. It could be damaged during extreme flow events, and its purpose is to reduce likelihood of dam overtopping. And the capacity of that spillway chute would depend on the hazard classification. So we need to, principal spillway, we need to safely pass the water. In Iowa, typically the principal spillway conduits, 95% in the inventory are conduits, pipes, bucks, something that's not a chute or a weir. So 5% of those are chutes and weirs, or 5% of the dams are chutes and weirs. Half of those are low head dams. So we've got a whole bunch of conduits and not many chutes and weirs. Concrete chute spillway requires expertise in reinforced concrete design. It'll need proper joint designs, drain systems. There's some resources from the NRCS, the Army Corps, Bureau of Reclamation, FERC, all have design standards for designing chutes. And you can find those in dam safety ASDSO. That damsafety.org is ASDSO. There's references there, and there's training webinars and seminars on designing spillways, or chute spillways. And then spillway conduits, the FEMA technical manual conduits through embankment dams is a huge, I don't even know how many pages, a few inches thick of reference material for conduits. FEMA technical manual on plastic pipe has recommendations for when and where and what types of plastic pipe can be used. That's from 2007. So there are some newer pipes that have been developed better joints and stuff that maybe aren't talked about in that manual. NRCS 378, Pond 378 has a good reference for designing small dams. And then NRCS TR 210-60 is a design reference for larger dams. Various material types could be concrete, metal, corrugated metal, steel, aluminum, welded steel, plastic, could be PVC, HDPE, depending on your hazard and use. NRCS 378 and TR 60. In general, 378 applies to the smaller dams. TR 60 applies to the larger dams. They have in the beginning of them, they list off which one applies to what size. Now the pipe inlet types could be a pipe that goes straight through from the water line to the outlet. Could have a bend near the end, or it could have no bend. The downside to it is there's less capacity, flow capacity. You have to get your water level up to the top of the pipe to get full pipe flow. It's an easier option to construct. The other type normally used is a drop inlet. So that uses a riser structure with using that weir flow around the riser. Bigger riser than the pipe gets you full pipe flow faster. It could be any shape, square, round, box, rectangle. It could be precast or cast in place. There's a NRCS design drop inlet spreadsheet on their engineering, Iowa engineering webpage that has a spreadsheet that will help you pick, or not pick, but it will show you when it's switches from weir flow to barrel to orifice to full pipe flow. We also need to look at the buoyancy of that riser structure and make sure it doesn't float, either when the water goes up or during normal pool. The typical Pseudos intake square intakes have a 4-inch concrete base that doesn't always meet the buoyancy checks. So sometimes those need modified to have a little bit bigger base or some more reinforcement. Sometimes. Concrete or conduit shapes for cast in place, you could make it any size. Much higher design effort, much higher labor costs to form that up. Could be round, square. Precast pipe is very commonly used on smaller dams. It's much easier to just lay out the precast pipe than form up this double box. Circular pipes are not perfect for dam design. Underneath the bottom side of that circle, how do you get compaction under there? Can't really easily. If you don't do enough compaction, you get voids, loose material that can cause seepage to start and give it a flow path. Too much compaction and your whole pipe will either lift up, move over. That will also give you voids and a seepage path. There's an example from a FEMA manual showing that looser material underneath there where you just can't get the compactor to. Example of a piping failure. So the pipe bedding in the middle of the picture here is an example of a NRCS standard low hazard corrugated pipe bedding. It's just sit the pipe on uncompacted, less compacted material. The pipe sinks into it as you compact around it and tamp under the haunches. that works good for low hazard dams. But for a high hazard, significant hazard, concrete pipe would need to go on a concrete cradle or concrete bedding. The FEMA conduit manual has examples of the two. This picture here on the right is what they call concrete bedding. It doesn't go up to the spring line to the midpoint of the pipe. It just goes under the bottom section, whereas the concrete cradle would go halfway up all the way around to the spring line. The bedding should have joints at the pipe joints. So if the bedding or if the pipe is needing to move or the foundation settles or whatever, bedding moves with the pipe. And it shouldn't just be dumped into the trench and poured into a loose soupy concrete mix just to flow down your trench. You should be putting joints in there. The trench should be uniform and consistent, which is hard to do. Formed bedding sides is the best way to do that, although it's much harder to do the construction. The sides of the bedding need to be sloped so that you can compact into the bedding instead of with a trench. Trench typically, not typically, but it can be dug out so that the slopes are opposite of what this figure is showing. And then you get that same problem of not being able to compact under the pipe. You can't compact into that wedge that's covered up by the trench wall. Sometimes the trenches are specified to the smallest possible size to fit the pipe, and then you can't get people in there to clean out the trench. You can't get the concrete in there as easily. And I've got some examples coming up. Here is a trench for a high hazard dam. You can see on the right side of this, kind of looks, at least the walls are vertical. Maybe it's wider at the bottom. They did do some benching, which is good on the one side. Other side is less clean. Here it is zoomed in a little bit more, opposite direction, showing the supports of the pipe pipe was going to be laid on. Here's that same trench with the pipe in it. This guy barely fits. And it will be harder to get that concrete down through that shape and underneath the pipe. The conduit joints need to be watertight. The cast in place pipes should have water stops at the joints, and precast pipes should have gaskets. There's an example of some water stop and a pipe with the gasket getting installed. Seepage control shall be provided, or spillway shall be provided with the means of piping and seepage control. Is needed for conduits or penetrations through the dam. Anti-seepage collars can be allowed with appropriate design references. If you have a reference that says it applies to that size of dam. NRCS 378 does have a section on when you can use seepage collars and where sizing and where to place them, as long as it's not over a certain height. Here's an example of some dam breaches with spillways that had seepage collars. And they are difficult to compact around. Can't really get up close to the pipe to get your compaction. You can see on the right side of both of these other two pictures, hand tampers. Trying to get compaction in there takes longer, it's harder to do. There's some pre-manufactured seepage collars that are easy to install, like on a CMP. You can buy the half sheet, bolt them together, seepage collars. Makes it easy to put together. And another benefit that the seepage collars do provide is as you're compacting around them, they do provide an anchoring effect of holding the pipe in place while you're trying to compact around it. But that could be solved with some different anchoring techniques if you weren't able to use seepage collars. A drainage diaphragm is the state of practice for seepage control through dams. And that would be a sand layer constructed around the conduit to control seepage. It would catch natural seepage through the embankment, intercept cracks, and prevent movement of soil particles. So the embankment is the dark colored on the top of these pictures. As seepage starts, it transports fines and they get caught in this filter material, plugging the hole, and that keeps pressure builds up behind it, seeps more, and it fills up this space until finally that pressure gradient is big enough that the seepage should stop and stop progressing through the filter. The FEMA filter manual for filters for embankment dams from 2011 is the best practices for building filter designs and construction. There's some full day classes on learning about filters and what to do, and there's a whole bunch of time that we can't spend on filters in this webinar, but there's a lot of information in that document about when and why to use dam filters or drainage filters. It has a step-by-step procedure on what materials to pick. Based on your embankment gradation, it has some checks on your filter material and what sizes, D50 gradations, that the compatible materials are to be big enough to pass water, but also small enough to get plugged by your embankment material. Typically, the ASTM C33 concrete sand will meet those requirements for most clay embankment soils. So you might not have to, if you're doing a low hazard dam, you wouldn't need to go through the whole filter process with gradations and testing. The larger dams you should, just to make sure. It also works to go from embankment to filter and then test if you can put riprap on top of that, or will your sand wash through the riprap. You can also use it for that process. There is a Western Dam Engineering technical note that was developed by some of the Western and North states. I think Montana is the one that started it. They have about 18 issues of these that have about 50 topics in all of them. I have a link to where you can download them. One of them in their first issue was on filter design, and it's got 5 pages of a history, nice summary of a history, design, construction, some construction practices, and design references. And that's a good resource to learn about filters. Some examples of filters that we've received for designs. This one, the top plan view shows water on the left, flowing to the right. It's got a filter in the middle, surrounding the pipe with an outlet off to the left side. Sand filter outlet, so sand drainage outlet. This one flows into a tow drain, which it wouldn't have to do. And then outlets next to that on both sides. Here's a more simple
Okay.
design. Same thing, filter outlets, this one on the right side through a sand layer, and then it transitions into coarse drain fill and then riprap on top of that. Could have, sometimes we'll see just this sand outlet or a riprap covered outlet. Those are harder to monitor if you are having seepage because you can't really see the water or how much water is coming out. Sometimes we'll transition into a pipe and then you can monitor that pipe outlet. Here's an example of an older design from the NRCS where the bedding of the pipe was also the filter outlet. They've transitioned away from doing that and have switched to moving the outlet to the adjacent to the pipe instead of below it. We don't see many more designs like this with the bedding drainage diaphragm. Geotextiles are also talked about in that FEMA filter manual. The use of geotextiles should be limited in dams. It should be in easy to access locations, and the geotextile function is not critical to the safety of the dam. So they don't want you to use a geotextile fabric as a drainage diaphragm, like in place of it, or as a chimney filter. Because if something goes wrong, you can't get to it, you can't replace it if it plugs. But like in a tow drain, if you're going to wrap the material in geotextile, that's fine because you can get to it, you can replace it. It's not critical to the safety. Trash racks and anti-vortex devices. Spillways should be provided with an anti-vortex. Trash racks or other inlet debris control measures. There's so many different types that are used. Commonly, they are just one big design feature. It could be separated. Here's some examples of a few NRCS type inlets: hooded, canopy. Top left has I think this one's a hood or canopy, can't remember, with the trash rack bolted on to the pipe. The other type with this plate over the top to stop the vortex, trash rack, bars around the inlet. There's some standard details from NRCS that have this welded bar, trash rack to get you some dimensions and sizes. And then on the top right is a standard NRCS drop inlet with the trash rack attached to the drop structure. The spillway outlet should be stable outlets capable of handling design exit flow velocities. So usually that will be a plunge pool. That could be riprap lined or self-scouring basin, and could also be a concrete outlet. The plunge pool, and if it has riprap, should be designed for its use and expected velocities. The NRCS has a plunge pool spreadsheet for helping you design the shape, size, and riprap sizes based on the flows. And then the riprap should be placed on bedding, design bedding to make sure that the embankment materials aren't eroding out of it. Here's an example of a plunge pool with riprap. And then here's an example of a concrete outlet energy dissipation structure. Pipe sizes. We don't have minimum pipe sizes in Chapter 73. So you would get your minimum pipe sizes from your design reference. NRCS 378 and TR 60 have guidelines for minimum pipe sizes. Low hazard is about 10 inches, significant 24, and height 30. You should consider clogging and the ability to inspect the pipe when choosing the pipe size. Also, if you're, we took out the rule that you don't have to have 2-foot of freeboard on top of a freeboard design storm if you don't have an auxiliary spillway. So in this part, if you are designing a dam without an emergency spillway, you would need to have probably a pipe big enough that we don't expect clogging to happen during that freeboard storm. The NRCS TR60 has some guidelines on what pipe openings should be if you don't have an auxiliary spillway. So that would be a good thing to check for. Precast pipes. The spillway should be designed to operate safely for the life of the structure. So typically, pressure pipe is used in dams for concrete pipe. The ASTM C361 is a low pressure pipe that is commonly used. It's stronger than just your basic RCP. It's got better joints and better gaskets. And TR60 requires reinforced concrete pressure pipe for TR60 size dams. SUDAS has a pressure pipe specification that I think is similar to this 361. I think it calls out 361 pipe. The hazard classification is important when you're picking your pipe type. High hazard, we wouldn't allow just a basic RCP. You would need to use pressure pipe. And any of the concrete pipes would probably need to have a gasket, depending on your circumstance, but most likely you're going to need to use at least a gasketed RCP in a low hazard. The SUDAS reinforced concrete low head pressure pipe. Yeah, it is the ASTM C361 with the O-ring joints. Some of the issues with the SUDAS pipe is using the SUDAS specification, the bedding for the pipe. It says it needs uniform bedding, full length of the pipe, excavate the bell holes as necessary, and then you can use any of these types. So it allows the class 1 bedding material, which is a granular bedding, and that's not a type of bedding that you should use through a dam, just because the water would flow through the granular materials. It's probably not compatible material, so your embankment materials would wash into it, creating seepage, seepage paths, and internal erosion. You can, in that SUDAS specification, you can do trench formed, which isn't preferred especially for a high hazard dam. And that bedding material should extend up to the spring line. They do have a concrete bedding material type, which we have approved in the past. But I think you specifically have to call out the concrete type, or the type that uses concrete. Auxiliary spillways. If an auxiliary spillway is proposed, it should be analyzed, designed, and constructed adequately to establish and maintain stability during the passage of design flows. It's typically an earthen channel. Here's a plan view of a large spillway over on the right side of the picture, flowing around the dam. The auxiliary spillway is provided to ensure a clear open area that functions as expected. NRCS 378 and TR60 have a bunch of guidelines on sizes, shapes, depth, width, on what to use. But In general, the flow in the auxiliary spillway is expected to cause erosion during the freeboard storm. The spillway erosion should not lead to failure, but maintenance should be expected in that area when you have high flows. So how do we eliminate the erosion or limit the erosion? We will locate the spillway away from the dam wherever possible. If you can get it not next to the embankment, that would be a better spot away from the dam. Smooth transitions, horizontal and vertical, should be provided at the inlet, control crest, and outlet of the emergency spillway, so not having a big sharp 90-degree bend. They should discharge a safe distance from the toe, and the inlet and outlet should be located to minimize erosion damage to the dam or damage to buildings, roads, and other structures. Here's an example of a dam that has emergency spillway up on the upper end of the picture, and it flows into the stream on the downstream bottom left. But they added a separation berm to keep that flow from coming back against the dam. Sometimes it's useful to model expected erosion of the spillway. NRCS sites can be used for stability and integrity analysis of the spillway. And then WinDam from NRCS is a program that can evaluate the slope protection, overtopping erosion, internal erosion, or piping, but WinDam does not do the inflow hydrograph. So you'd have to get that either from sites or your own software. We have received WinDam to evaluate stability of the dam during erosion. This is an example of a dam that was, it was, for whatever reason, it had to go down in the very bottom corner of the property lines, and there was no way to get the spillway moved over closer to there's a road over on one side. Couldn't get a berm in there, couldn't get the spillway moved. So they did a WinDam analysis on the auxiliary spillway. You put in your profile of your spillway, different layers of materials in their profiles. There's a couple material properties that you have to put in: density, percent clay, and this head cut index. And then you can route the hydrograph through over that spillway, and it will initiate the failure of the surface, so your vegetative cover, and then start the head cut and see how far it progresses through the spillway as the hydrograph goes through time. In this case, the spillway didn't breach before the storm was over, so this showed that this spillway was stable, or not stable, but the spillway could handle the erosion. It would need maintenance, it would need repaired after a storm. They had the geotech reviewed this analysis also, and the stability of the dam after the material was eroded. It didn't meet factor of safety requirements, but it still was above 1, so still was standing. It wasn't causing failure of the dam. And now, if we have any questions on spillways before we move on to embankments.
Just one came in early on about seepage collars, but then you started talking about seepage collars, so that was covered up. Someone asked about the slides. available to download. Did you get those posted yet?
I did put those in
I
the
don't-
chat.
I see dam rules, earth embankment dams, dam design handouts. Is that what
Dam
that contained
design
the slides?
handouts is the slides, yeah.
Okay. Hopefully that answers their question. So that, yeah, that handout that says dam design handout should include the slide. Anybody else? Anything on your minds? Oh, got another one. Can the auxiliary spillway be protected with concrete or riprap?
Yes. Yeah, it doesn't have to be vegetated. It could be TRM, could be riprap, whatever is needed to protect that slope. Riprap
Yeah.
would be harder to maintain and harder to keep brush and stuff from growing in it, but it can work.
Right. Yeah. I mean, anybody who's dealt with even riprap wave protection will realize long term that keeping one thing we're going to get on you for on inspections is keeping the vegetation out of that riprap. So it's gonna, every year or two, you got to get in there and start clipping that some woody, especially the woody material. Grasses are okay, but woody material. So a couple questions came in relative to each other now about, yeah, so there's a picture, yeah, riprap. I mean, early on, I guess if the riprap's thick enough, usually stuff doesn't grow in it right away, but over time, as you get some material filling in there, vegetative material, then things start to take root. So those need to be sprayed or cut. So same thing with a large area of auxiliary spillway. Plus, it's riprap's expensive as well. So if you can design your auxiliary spillway without it, that's ideal. Casey mentioned TRMs, turf reinforcing mats. There's a lot of products out there that promise a lot of things. A good installation is critical for those, because if there's a lot of failures that can happen on those turf reinforcing mats when they're not put in as perfectly as the testing that went on them with. So if you're ever thinking of a TRM, make sure you look into the research, the testing that they've done as a company and what conditions those testings were under, how they're anchored, how they're properly installed, and does it rely on a good vegetation? Sometimes that vegetation doesn't come in through them as well as it needs to. So if TRMs are your sole source of meeting criteria, we'll probably have some scrutiny on that. So there is some questions about, you sort of touched on the 2-foot freeboard rule change. And then another one that kind of goes along with that is that we don't require additional freeboard if but the designer should consider plugging blockage in its design. Is that correct? So I guess, yeah, so previous rules, it was just in our requirements at the DNR that if you didn't have a secondary spillway, an auxiliary spillway, and solely, let's say, a pipe, especially, as a safety factor, it required that you raise the top of your dam 2 foot above the freeboard design storm to account for the risks associated with maybe your principal spillway, your sole spillway piping or failing. That's gone away in the new rules. However, that design is going to be scrutinized a little bit more, like Casey said, to make sure that that risk isn't there. So maybe it's an open chute spillway, because we used to give a lot of waivers for dams that had one spillway, but it was an open chute concrete spillway, right? Risk of clogging of an open chute concrete spillway is very rare. So we felt that additional freeboard could be waived. We would do waivers on that. That's a good example of one that would work well. But otherwise, yeah, maybe we're looking at, do you have a 4-foot, 5-foot diameter principal spillway? Something that's, you know, quite substantial, especially if it's a high hazard dam. And maybe a well-designed inlet that can minimize clogging and trash rack. And I don't know if you want to add to that, Casey, as far as the freeboard single spillway.
Yeah, no, I think you hit it all. We don't have a specific rule that says what to do, but the rule that covers it is the one that says spillways shall be designed to operate safely for the life of the structure. So if you don't have an auxiliary spillway, then we need to see the way that it operates safely is by not clogging.
And sometimes too, just the where the dam's located and its watershed.
Yep.
Some have a really heavy, say, log and load that can come down if it's a real heavily wooded upstream watershed or creek corridor that's always, you know, dropping trees into it and coming down, or if it's you know, more urban landscaped. I mean, there is some risk of a swimming pool or something coming down, or, you know, some kids' toys or something, but you're not going to have as much debris maybe in a sometimes in an urbanized watershed. So sometimes that plays a role too on just what is the clogging risk can be looked at and considered.
Yep. And some of those heavily wooded areas, they'll build trash racks up the
Mhm.
stream to catch the logs before they're coming in.
Mm-hmm. Yeah, and back to John's question about the freeboard. So really, we don't worry about flood clogging as much if you're adding an auxiliary spillway. So what we're talking about is if you're had a single principal spillway and then ran your freeboard design storm up to the top of the dam. That's where we're going to scrutinize a little bit and make sure that we don't have that plugging risk and overtopping potential. But if you've got a large auxiliary spillway, open chute, you know, grass lined or whatnot, then we're not going to scrutinize the plugging as much, because usually by the time you get the freeboard design storm, the principal spillway, the amount of water that's taking on isn't as, I guess it depends on the design, but usually that's not quite as critical because most of the flow on a freeboard design storm is going to go out the auxiliary spillway. And then a question about what to use under riprap to prevent erosion. What are different bedding designs you've seen?
Yeah, that could be, it could be going from embankment to a finer material and then transitioning to bigger riprap. Could be a couple stages of granular material. You could do a matte geotextile if it was like the shoreline. That's pretty common to have the geotextile with riprap on top.
And once again, there's probably some riprap design guidance we can get out there too. And I'm gonna, if you have time at the end, Casey, I'm gonna plug the ASTSO's new dam design toolbox reference website, which is going to be a great resource for folks too. So, all right, I think that's it for now. So,
okay,
can keep going.
Sounds good. Thank you. Next is, let's go to the embankments. So we have the spillways to safely pass the water. Now we need the embankment to safely hold water. The applicant shall document design standards, design references. I won't read the rest of that. But those different features are the prescriptive features that we took out. So top width, core trenches, what kind of material, thicknesses. Those are all things that you do need to design for, but we didn't print them in our rules to say you have to meet these specific things. We just want to see your design reference that shows what you picked, why you picked it. Typically in Iowa will be a homogeneous fill, not, as this example shows, a clay core with earth around it. We don't usually have an embankment dam built with two materials. You just use the one which you get on site. Guidelines and embankments, 3:1 is recommended usually for maintenance. And your different design references will have a settlement allowance. Usually that's about 5% from your constructed fill to your settled fill. That usually occurs during construction. So you don't. Sometimes you can reduce that if your geotech analysis or geotech report says something less because that settlement was occurring during your construction process. The top width usually is from 10 to 14 feet, depending on how big your dam is in hazard classification. Core trench on the embankment provides a cutoff through the foundation. Make sure you're not finding some other material as you check vertically down. It extends longitudinally into the abutments, and you should extend it into impervious fill. So if you're finding granular sandy materials, you should keep excavating. Make sure to get that cut off into impervious materials. Wave erosion should have a bench or a berm. Sometimes it could be lined with riprap to help prevent some further erosion. Here's an example of a kind of a bench with riprap. But as we were talking about riprap before, it's hard to keep brush and stuff out of that material. Site preparation is important for the footprint of the dam. You should get the organic matter removed, your topsoil, grasses, trees, whatever. All that organic material should be not in the dam embankment. The surface should be graded to remove discontinuities, so it's a flat surface or at least not a wavy, rocky surface to compact into. The fill material should be clean earth without vegetation and rocks. Fill placement, the design references will have your lift thickness, maximum lift thickness based on what you're using for compaction. Moisture content might need to be adjusted to get better compaction. Smooth steel rollers and caterpillar tracks generally don't provide adequate compaction. And you should place and compact your earth material next to structures carefully to not move them or damage them. And then seeding, you should seed as soon as possible after construction, and it could be a native or it could be a lawn mix. It doesn't have to be a mowed golf course looking surface. NRCS 378 and TR 60 are great resources on embankment designs and what to use. TR 60 will have more guidelines on stability for your larger dams, different factors of safety to check for throughout the life of the dam. Drains are not normally required on significant and high hazard. Wait, they normally are, sorry. They're not. Drains are normally required on significant and high hazard dams. It could be a chimney drain, a blanket drain, or a toe drain, or a combination of any of those. Here's some examples of a chimney. The top picture has a chimney filter, so that will go, instead of just a drainage diaphragm at the pipe, this would be the whole length of the embankment. Chimney filter usually would go up near the top down to the bottom. It could drain into a blanket filter, which drains the toe or the lower surface of the dam. That could even drain into a toe drain to pick up your foundation seepage or any piece of any of those. The The middle picture doesn't have the chimney, but it has a blanket drain over on the left. And then this last third picture on the bottom is it's an existing dam that has a chimney filter added onto it and a stability berm placed on top of that. So that would be a remediation type project. A single stage filter may not drain the quantities of water that maybe you're expecting. So you might need to add a coarse material inside, or a pipe inside of that filter material to get your flow moving. Those materials would need checked for compatibility, which the FEMA filter manual goes through those 7 design steps on how to check your materials compatibility. Some special requirements for high and significant hazard. These are the dams that used to be called major dams, but now we've switched to just requiring it for all high and significant hazard because of the size, importance, hazard. We might need a higher level of investigation or design. And these would be the NRCS Tier 60 size dams, and 378 wouldn't apply to designing these high and significant hazards. It would need a soils investigation. So you need a geotechnical engineer to look at slope stability at the end of construction, steady state seepage, and a sudden drawdown. We would look at anticipated settlement, seepage, the potential for seepage through the embankment or under or around the embankment, and some construction practices for the soil types. Tier 60 has great criteria for these things. So that's a good design reference to use. The anticipated sedimentation should be investigated. NRCS again has sedimentation rate assumptions. A gated low level outlet shall be provided, and it needs to drain 50% of the permanent storage within 10 days. A dam breach analysis may be required to show what is the risk downstream. Is it make sure it's not being underrated, and might be needed for the high hazard to show what's at risk downstream. Construction shall be inspected under the supervision of a licensed engineer. For the high and significant hazard dams, we want to make sure that it's being built the way that you intended it to be designed. And some critical phases that should be looked at, or at least watched during construction, is the foundation prep, the outlet works construction, any testing of materials, make sure it's happening, make sure it's working as designed, and then internal drainage features, filters, diaphragms. Also for high hazard dams, an emergency action plan is required for those now in Iowa. It's a plan that documents emergency conditions at the dam, what you would do, what things to watch for as the dam owner, who they would call, who they would contact, and what the next steps are to help minimize property and loss of life damages. The DNR helps assist dam owners with these. That would include a breach map for the high hazard dam to show who would be affected and if notifications or evacuations are needed for the emergency management. These are developed with the emergency managers and the downstream communities, along with the DNR and the owner. And it's the owner's, the emergency action plan is the owner's document to maintain. What do they do? The specifications for the dam design will describe the approved work methods, equipment and materials and end results. Typically, they're a separate document included with the design plans, but they could also be on a smaller project, they could be just put in notes on the design sheets. And that does happen kind of commonly. The specifications, many times it seems they get submitted without being, they get rushed through. Maybe they weren't looked at super closely. So it helps if you can take a read through them before you send them in. SUDA specifications are not always applicable to dam construction. Sometimes they are, sometimes they're not. The NRCS has a set of specifications that are a good resource. These are on the Iowa Engineering NRCS page. And there's a link there to them. These are specifications to be included with the design. So it's, or with the plans. It's not a standard design that you can just reference Iowa 3. And everybody knows what that means. They're intended to be modified or changed, but to be included with your project. And those will cover everything that you should need for a basic dam design. Operating plans might be required if there's any gates or movable structures that are needed to operate during a flood or to pass the flood. So, but it would need to be if you have to operate it to pass the flood, not just if you have a gate. That operating plan would identify who's responsible for operation and maintenance of the dam and the gates or structures, whatever needs to operate. It would go through in detail the sequence of the openings, the rate of the openings, and what you would do during low flow situations or during refilling. And then lands and right-of-way easements. The same list of easements and ownership is in the rules that we had in our prior rules. We won't read through them, but the dam needs to be on your property, or you have to have permission to be building it there. You can pool water on your land, or you have to have permission to pool it on somebody else's land with easement or ownership. And then future land use could impact the hazard classification. If you're upstream from a city that looks like it's developing, it looks like there's going to be development down below the dam, we might upgrade it during design to account for that, to significant or high. The design submittals, make sure on the specific wording of the rules in the design source. So shall, required, recommended, guideline. Shall and required is what's used in our administrative rules. You need a variance according to a different rule section. You can have a variance request form that you would need to fill out to change something that maybe doesn't apply to this case. And then in the design report, we'd want to see justifications for deviation from guidelines or recommended guideline should types of criteria, which won't be things in our rules, but it will be from your design reference. The preliminary and final design report should summarize the dam design, have hydrologic calculations, geotech report if needed, and discuss the deviations from any criteria. And then we have a dam inventory water storage information sheet with a checklist that you can submit. The preliminary and final design plans should have the embankment details, elevations, spillway, profile, cross sections, anything needed to show what you're submitting for. The preliminary design, I'll switch to this. Here's the form that has the checklist that you would submit with your application for the preliminary and and then add for your final submittal. We'd want to see your design report, any H&H calculations, hazard analysis, basic design drawings to review your hazard class and your hydrology information in that preliminary submittal, and then final design. If there's any changes, get your final plans, final design report. Here is a screenshot of that sheet. Just has basic name, location, purpose, elevations, information that we put in our database for the DM. This also has the information on where you pay that $75 fee. Right now, you still can call in or mail a check. And that, I didn't put it in the slides, but that preliminary submittal is where we would want to agree on the hazard classification specifically. That's the biggest part that we usually need to talk about before any of the complicated dams that are just not a basic farm pond. And then the ASDSO Training Center has different topics that you can look at, different seminars, webinars, and different design references. Permit application for your application for doing the permit is in a system that we call Permit. There's a link to it. You can submit your joint application to the DNR, Sovereign Lands, and the Army Corps. You can also request environmental reviews, BFE, declaratory orders, and then you can view and track your status once you have applied. And you also submit your information for the application in there. And we also issue our permits and store the files in that same system. When you're applying to submit the permit, you pick a project type. If you're designing dam, you would pick dam. It would give you this box. It asks you some questions about the height, storage, and is it high hazard, basically. And this is a screening tool to tell you if you need to apply for the dam permit if you exceed those thresholds. If not, it might tell you no, as long as you're out of the floodplain, regulated floodplain. Then it would tell you no permit needed. Otherwise, you might still need to apply based on your location if you're in a larger drainage area. You pick your location, where you're going to build the dam with a line, point, shape. You could draw whatever shape you wanted to there. Hit get results, and it will tell you yes or no. And then if you want an official response from the DNR, you need to fill out the joint application. Some additional resources, the ASDSO. It's a great resource for dams. It's open to all owners, consultants, and state officials. There's general public resources, damowner.org, damfailures.org has different resources for dam owners. That damfailures.org has a bunch of different case studies on dam failures, lessons learned on various dam failures, new, recent, and older. We'll get this posted on YouTube and the website. And then also this ASDSO Dam Owner Academy is a newer series that they've been creating with a bunch of different topics on dams and planning. And these new ones down at the bottom are really good about plants and animals, dam failures, seepage. We will get completion certificates sent out to everybody that said they wanted one during registration, or if you pick no on accident, let us know. We'll get those sent out soon. And if you have more questions, you can answer those now. And I think John wanted to say something about the reference, ASDSO reference toolbox.
Yeah, so let's see. Question about outlet pipes. When using a granular filter diaphragm around an outlet pipe, can you use a slotted collection pipe under the diaphragm and a solid pipe out to the toe, or do you need to use a granular drain out to the toe?
Yeah, you could, yes, all of that. You could have a slotted pipe inside the filter to get the water in that pipe and then transition to a solid pipe. That would make it easier to monitor. You could get seepage around that pipe, but it would be at the toe. So it's a good way to be able to monitor seepage if it's occurring and be able to measure it.
All right, that's it so far. Maybe I'll share my screen quick. You wanna?
Do I stop?
I think so, or I don't know if I can just do it. Let me get things arranged here real quick. And if you have more questions, go ahead and start typing them in, but this is kind of, so Casey gave a great overview of button, oops, not use Zoom as much. Okay. All right, hopefully you can see my screen here. So yeah, Casey gave a plug for ASDSO, and like he said, it's a great organization for anybody involved in dam design, even though the name kind of implies it's kind of formed by the state, but a great resource for everyone. And a new tool, kind of hot off the press, this has really just gone public. It hasn't really been highly marketed outside the ASDSO community yet, but really is kind of becoming in a great final form almost. It's as we've talked today, you know, you can tell that we have a lot of resources in a lot of different places, right? There's a lot of great national organizations like NRCS or the Army Corps of Engineers or ASDSO, FEMA, et cetera, right? A lot of great dam design standards out there. So would it be great if we could have them kind of in one central place? And that's the inspiration behind this dam safety toolbox that ASDSO has put a lot of resources in over the last year or so in developing this. So this is a great website called damtoolbox.org, and it's a wiki. So the idea is this will be a living document that if you want to get involved and help, anybody that's an ASDSO member can actually go on this page and make suggestions. You do have to have a membership, a login to ASDSO to do that, or there's a box at the bottom, I believe, that says contribute. And if you see something on here that says, hey, I don't think that's right, or I know of a better document or a resource, you can suggest that and it'll be updated as time goes on. So that's kind of what's great about it. So yeah, anybody can use this right now, but if we click on like hydrology, it's going to give a little intro on that topic. And it's going to have various more in-depth pages, and then it's going to have reference documents included. And so right there at the top of the list, TR 21060, which Casey's mentioned a lot. As you can see, it is a great national resource, not just from our words, but some other FEMA documents out there. So this is, and then some training documents. So this is really an exciting new resource that hasn't really been shared too widely yet. And it's got a lot of other dam safety management stuff too, but on the technical side, it's meant to be a place where you can dive into double checking, you know, am I using the latest and greatest best practices out there? You know, what are the things I should double check for my dam design? And that's what we're kind of looking for as a state. As a state agency, we can't always keep on top of things. So this also helps us too in reviewing designs and pointing things out to consultants making sure that you guys are aware of the best design practices and resources out there. So feel free to take a look at this. Like I said, it's essentially done. I think it'll be kind of fully revealed at this year's Dam Safety Conference in September. But it's basically live now and kind of ready to go. But it'll be continually added to and extended as time goes on, is the idea. It's a wiki, just like Wikipedia. Anybody can go in and make suggestions. This one has a little more moderation capability. No one can just go in and make a change. Even if they are an ASDSO member and they suggest a change, it kind of gets stored behind the scenes until a moderator has reviewed it and says, oh yeah, that's a good one, and make that switch. So yeah, I guess and it's got some other great background stuff too on just dams themselves. But hopefully you guys find this useful, and if you want to get involved in maintaining this, there's a group that does that through ASDSO. So I'm on that work group and committee. So reach out or feel free to get involved in helping. If you're a subject matter expert in one of these items, they're always looking for help on maintaining these pages. So that's my plug on that. With that, don't see any new questions. Someone asked about the PowerPoint, and yeah, it's going to be that dam design handouts PDF that will contain the PowerPoint slides. And then, like we said, we should, hopefully everything went well with the recording on this, and we'll be able to post it and link it on our dam safety page here at the DNR. So if there's something you wanted to go back and rewatch. So just a couple minutes left. If anybody has a final question, we can talk about it. Otherwise, good timing, Casey. Landed right on the 2-hour mark. It's always hard to judge, right? So, all right. Well, thanks for putting that together, and thanks everyone for joining us today. And we'll talk to you all later.
That's good. Thank you.